What's going on, everybody? This is Mr. Diamond, and this is going to be an introductory video for our last section of Chapter 3, Molecular Geometry. Now, there's a very small amount of notes for this section, and then we're going to be getting into some structural drawing, and I'm going to actually switch over to HandCam to do that. So to start with, molecular Lewis dot structures are a little bit more complex than their ionic counterparts. And by a little bit more complex, I mean like worth double the points on the test, more complex. Not only do they form bonds instead of just being kind of stuck to each other, but you almost have to solve like a puzzle to figure out exactly how they're connected. Sometimes they have double bonds or triple bonds. Sometimes there's resonance. Sometimes they're polar. Sometimes they're not. And we also start caring about the geometry of bonds now. So there's a lot that goes into this. But I want to tell you before any of you get kind of freaked out about this, a lot of this section is if you like kind of like I said back on the ionic or isotope tables. It's kind of like that, where it's a lot like it's like a puzzle that you're trying to solve, and you have a certain amount of information, and you have to make logical deductions based on that information to predict the outcome. So you'll kind of see what I mean whenever we get into our example problems. But molecular geometry is the 3D arrangement of an atom's position in space. That's how we describe it. It's determined through the Lewis structure, but also is based on what's called VSEPR theory. I know that's not an E before that, but it's VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion, which seems really scary, but if we just break down all of those words to what they mean, you'll hopefully realize it's not actually that bad. Valence shell is outermost shell of electrons, so this is just saying it's the outside electrons. And it's pairs because electrons come in pairs. So all of that is really just saying, hey, the pairs of electrons on the outermost layer. So the stuff you've been already using in a Lewis dot structure. That's what this whole first piece is just saying. And then it's repulsion. Now, repulsion is probably something you've felt at some point in your life based on seeing something absolutely disgusting or horrifying to you. But in this case, we're talking about like actual electrostatic repulsion. So we got like positives pushing away each other, and in this case, it'll be negatives pushing away each other. So if you have two negative things, if you have two sets of electrons that move close to each other, they're going to want to push apart. Negatives don't want to be near each other. Like things repel, and dislike things or unlike things attract in the form of, or in the realm of, electrostatic attractions. So VSEPR theory is based on the fact that electrons actually have to take up space, and they take up most of the volume of an atom, but because they're negatives, and a negative will repel each other, bonds of shared electrons, that means that bonds and electron pairs are going to try to stay as far away from each other as possible. And because we know that there's this 3D sphere, if we know how many bonds and how many pairs they are, we can predict, well, what's the optimal position they can be in to where they don't interfere with each other and they can actually stay a certain amount of distance away. And so that one fact, the fact that bonds are made out of electrons are negative things, if you have two of them, will repel each other. Those three things make sure my fingers are on screen. Those three things together combine together to give us all of how we decide molecular geometry works. When we look at molecular geometry, we care about what is called steric number. Steric number is the amount of groups connected to an atom. Groups can be a pair of electrons or a bonded atom. It just depends on the steric number. We can look at our data table, which is a table of information that you're going to be given, to predict the geometry. And we'll get a lot of practice with this in class. There should be a link to this table on Google Classroom. I'm going to pull it up in a moment. I'm going to have, after I pause this and kind of look at it and talk about it, and then we'll pause after the notes, go to that, pause after that, and I'll start out working out examples. Or I may make that a separate video. We'll make that a separate video so it's a little easier to follow. So here's the steps for drawing a molecular Lewis structure. It's 5 steps, but there's really a lot. First, count the total number of valence electrons, including charges as needed. So count how many electrons would all of them have. If there's a charge, if it's negative, you add more electrons. If it's positive, you remove that many electrons. Then you connect all the atoms with single bonds to the central atom. Central atoms are usually listed first, unless it's hydrogen. Hydrogen only wants to make one bond because helium, remember, helium has 2 valence electrons, so to have a full octet or a full outer layer, helium actually only needs to have 2. And since hydrogen has 1, it's already halfway there. Hydrogen's only ever going to bond to one thing, so it never gets to be the center. Everything else, though, every other time you just look at what's first. If it's not hydrogen, you go to the second thing. That's going to be your center atom. Then you give electrons until all of the outer atoms are happy. And in this case, happy means an octet because atoms want to have a full outer layer. Unless it's hydrogen, again, hydrogen only ever wants to make 1 bond. It only wants to have 2 electrons total. You put any leftover electrons you have on the central atom. And then if the central atom isn't happy, you make double or triple bonds with outer lone electrons. I've tried to avoid this usually. Most of the time we've had exceptions that are hydrogen or helium or something like that. But in this case, there is one exception for one other element, and that is boron. Nobody likes boron because it's really unreactive, so you don't actually have to care if boron is happy. Boron is the one element on the periodic table, as far as we're concerned at this point, that you actually don't have to be concerned if boron has a full octet. Every other center atom is important enough and we care enough that they get a having full octet, but boron you do not have to care about. Now, the other things you're going to have to do is involve predicting polarity. There's 2 major ways to predict that something is polar when you look at molecular structures. After you do this enough, you'll be able to just kind of look at it and figure it out, but there's 2 strategies you're really going to look at. First, and the easiest, is does it have a pair of unbonded electrons? If it has a pair of electrons, it's polar, no matter what. Doesn't matter if it's 1, 2, 3, however many unpairs or pairs of unbonded electrons. If there are lone pairs on the center atom, it is immediately polar. The second thing is it asymmetrical? And what I mean by that is, does it have different types of groups bonded to it? Like, for example, if it has 1 chlorine and 1 bromine, yes, it's got to be polar, even if it doesn't have dots in the middle. Or let's say it's got 3 hydrogens and 1 of a bromine on something. That bromine is going to have a higher electronegativity and therefore is going to pull electrons that way, and it's going to make it polar. Even though it looks symmetrical, it has to be exactly identical. It can't just be kind of identical. Finally, we've got resonance. This is a topic that will come up more if you take organic chemistry. Sometimes when you're drawing a structure, you'll actually run into a problem where you don't know where to put a double bond. You could put it multiple places and it would still work out. So when that happens, you have resonance. Resonance is a spreading out of electrons. It's used when one Lewis structure can't accurately represent a molecule. And we'll do an example of this with ozone, and you'll see what I mean in an example we'll get to in a moment. I'm going to pause the video real quick, and then I'm going to pull up the sheet, and I'm going to explain a little bit more about steric number. It may not make a ton of sense right away, but when you watch the attached example videos that should be down on it's not YouTube, I can't point to a direction. It should be a link with this on Google Classroom. All right, welcome back. So this is the chart. Now, I'm going to go ahead and show you there is more to this, but we're only concerned at this point with this top part of the chart right here. So over here in this column, we've got steric number. There's 2, 3, and 4. And then it's got the 0 lone pairs, 1 lone pairs, or 2 lone pairs. That's all you'll have to be concerned about. There won't be anything else this direction. So the first thing that you'll notice is that each of these columns only really has, like, as you increase steric number, the options increase as to what you can have. So, for example, right here, this is a linear atom, and it happens when the center, whatever the center is, and in this case, E is representing the center atoms, it is bonded to 2 things, and there are no dots. So 2 things it's bonded to means it has a steric number of 2, and there are no dots on it. This one right here, that's called linear. This is trigonal planar. Trigonal planar is when it's bonded to 3 things, 0 dots. Now, again, it says bonded to things. These could, and it's showing single bonds. This could be a triple bond here and a single bond. This could be a double bond and 2 single bonds. It doesn't really matter how many lines there are in the bond for these. It's just how many connections to atoms does it have. Now, if one of these was replaced with a pair of dots instead of an atom, you would then have bent or angular. And we call this rare bent because it's much less likely to actually occur. And it's going to change the geometry very, very slightly. So this was 180 degrees. 120 degrees is the optimal arrangement or optimal distance away you can be for this. But as you'll see in the example videos where I kind of work it out, this is actually going to be slightly less than 120 because these atoms or these electrons are going to push these groups down a little bit. And if from here your brain might say, okay, well, if there's 4 things, my brain says that it should be 90 degrees apart. But you have to remember that we have 3D arrangements. These are 3D, which means they actually can get further apart than 90 degrees. They can form what's called a tetrahedral shape. So if you have 4 things and no dots, it forms this tetrahedral arrangement that has 109 degrees as its angle. If you take one of those things away and you have a pair of dots, it becomes trigonal pyramidal. Notice this was planar. It's flat and it has 3 things. This one has a pair of dots in the middle, and that makes it pyramidal. And that's the way I recommend that you remember it. And if you have 2 pairs of dots and 2 things, then that's called bent or angular. We don't call that rare. So this is rare bent. This is normal bent. And notice that as you add dots, it kind of pushes and it makes the things that are normally here, if there was a pair of dots right here, every time you add one, the things kind of bend away and they try to avoid it. And it makes the angles slightly smaller as these groups get closer together. Same thing happens right here. Now again, as I apologize for my yawn. Now again, this is a little bit more confusing by just seeing it abstractly. In the next video, I'm going to have the camera faced my hands, and I'm going to have my molecule kit, and it's going to hopefully make a lot more sense as to how this stuff is actually going to work out with the examples that I'm going to do. So that's going to be it for this video. I hope that makes as much sense as it can without watching the example videos. You really should watch that like very soon after this, otherwise it won't make a ton of sense. In the meantime, though, this is Mr. Diamond signing off. I hope you have a good rest of your day, everybody, and I hope to see or hear from you soon.